We're going to be working a problem where we figure out the molar mass of an unknown substance. So I have a problem up, so we're just going to read through it, and then we'll work step by step to figure out how to correctly solve a problem such as this. So we have the situation. We have a forensic chemist. They receive some unknown white powder, and they need to identify it and figure out if it's a controlled substance or not. And controlled means illegal. So this chemist, she dissolves 0.483 grams of the unidentified substance in 8.00 grams of benzene. And the solution that creates freezes at 3.9 degrees. The freezing point of just the pure benzene solvent is 5.5 degrees. And the freezing point constant for benzene is 5.12 degrees Celsius per mole. So if we just look at that information, the first thing that you would need to do is you want to try to organize the data so that you can see what you have and what it belongs to. And one of the things that I recommend is when you have a solution that you separate the information into solution information, solvent information, and solute information. And so I'm going to take the time and just jot down the information and just characterize it. Is this solute, solvent, or solution? And so my solute is an unknown solute. So I don't know the formula, I don't know the molar mass, but I do know the mass of it, and I do know that it dissolves in benzene. And my solvent is benzene. And then when you dissolve the unknown solute into the solvent benzene, you get a solution. So benzene is an organic solvent that is non-polar. So if this substance can dissolve in benzene, it must also be organic and non-polar. That's going to be important information to keep in mind. So if we look at our information, we have 0.483 grams of unknown solute. And we know we have 8.00 grams of benzene. For the solution, we know that the solution freezes at 3.9 degrees Celsius, and that's the freezing point. But we know that the benzene normally freezes at 5.5 degrees Celsius. And we know the constant for benzene is 5.12 degrees Celsius per mole. So that is all the information that we have, and somehow using that information we should be able to translate that into information to figure out what this unknown substance might be or what it might not be. So we have a freezing point for a solution, and anytime you have a freezing point for a solution, that's a colligative property. So there are two equations that we use with freezing point, and it's a property called freezing point depression. So when you make a solution with some kind of non-volatile solute, the freezing point of the normal pure solvent goes down when it is in a solution situation. So the solute causes that freezing point to be depressed. And so we have two equations that we look at. If we know the freezing point of the solution, that will be equal to the freezing point of the pure solvent minus some change in temperature. And this change in temperature is proportional to the molality that's in solution times Kf. And here I didn't put the I factor. So if I put that back in there, I is the number of particles that gets created when the solute dissolves. For our substance, it is some organic substance that is nonpolar. Therefore, it's not going to ionize. So the I will be 1 because it is in an organic solvent. So if we take this information and we also take our equations, the freezing point of the solution is 3.9 degrees Celsius. And the freezing point of our pure solvent is 5.5 degrees Celsius. So I've used this number and I've used that number. So I'm just going to cross it out so I can see that I've used it. And that will be how we figure out what our delta T is. That is the change that this freezing point underwent when the solute was dissolved. So if we rearrange, we take the 5.5 and we subtract the 3.9, and we get a change in temperature of the freezing point of 1.6 degrees Celsius. This value, we plug it in to the second equation, which is the change in temperature for the freezing point is equal to the molality times the constant. And so if we plug that number 1.6 degrees Celsius in here, since it's an organic substance that's nonpolar, the I factor is 1. Molality, and then the constant is 5.12 degrees Celsius per molal. By using this second equation, we can answer the first question, which is, what is the molality of this white powder? The molality is the moles of the unknown white powder divided by the amount of benzene. So when we rearrange this, we're going to divide both sides by 5.12 degrees Celsius per molal. Degrees Celsius cancels, and we will end up with molality as our leftover unit. So we have 1.6 divided by 5.12 equals 0.3125. And I'm not going to round right now because this is not the final answer. We're trying to get to another answer using this number. And so we find out that the molality is 0.3125 for our concentration of that unknown substance. So what does this molality tell us? Well, molality is the moles of substance divided by the kilograms of the solvent. So for our substance, our molality is this 0.3125 molal. Moles of substance, I do not know that. So here's what I do know. I know that I have 0.483 grams, but I don't know how many moles that is. And so I don't know moles. I also know that I have 8 grams of benzene. Well, benzene is my solvent. And so if we look at the definition here, kilograms of solvent is the bottom number. So I can take my molality and I can set it equal to the number of moles of our unknown, because that's my solute, it's on top, and I can divide it by the known 8 grams of benzene. So I'm going to cross this out. but I need it to be in kilograms because the formula is per kilogram. So on the bottom, I'm going to put 0.00800 kilograms of benzene. So from the molality definition, I can figure out how many moles of my unknown substance I have. So I'm going to rearrange this equation, and I'm going to take my molality and multiply it by the number of kilograms. 0.00800 equals, and I get 0.0025. And that's moles of unknown solute. So now this is a piece of information that I now know about my unknown. So I know that I have 0.8483 grams of unknown, and I know that that amount is also in moles 0.0025 moles. So this second question, what is the molar mass? Normally we have grams, we use molar mass to get moles. But now we have grams and we have moles. So if I can use molar mass to get to moles, then I should also be able to use grams and moles and get to molar mass, because molar mass is simply the ratio of the number of grams you have divided by the number of moles that equals. And so if we look here at our data, we have the number of grams and we also have the number of moles. So if you have the number of grams of a substance and its number of moles that equals, then you can divide the two numbers and that will give you the substance's experimental molar mass. So I'm going to take these two numbers and I'm simply going to divide them by each other. And so we have 0.483 divided by 0.0025 equals, I got 193.2 in the unit grams per mole, because those are the two units right there. They don't cancel. If we round it for significant figures, this should be a 0 here, we got three significant figures, so the molar mass is about 193 grams per mole. That number makes sense because molar masses are relatively large values. So you wouldn't have decimal numbers for molar masses because all of the molar masses of every individual atom are 1 or greater. And so our molar mass is about 193. That's the second question. Now, the purpose of this experiment that was done by the forensic chemist was to figure out, what is this substance? Is it possibly one of the common unknown controlled substances? So we have a list here of unknown substances that they could be. So we've got cocaine, we've got methamphetamine, ecstasy, heroin, morphine. So we have the chemical formula. So we have the total number of carbons, hydrogens, nitrogens, oxygens that each of these contain. So if we take each of these and we write down the formula and we figure out its approximate molar mass, and we just need it to the ones place, since this molar mass, we rounded it to the ones place by significant figures. So cocaine has a total of 17 carbons, 21 hydrogens, 1 nitrogen, and 4 oxygens in a double ring situation. Okay, so if we have 17, and if we just use about 12 for the carbon, we have 21 hydrogens, and each one's about 1. We have 1 nitrogen that's about 14, and we have 4 oxygens that are around 16. We get a total of 303 grams per mole. Okay, so ours was 193, 193. So that one is not going to be cocaine. Then we can move on to methamphetamine. And its formula, the molecule has a total of 10 carbons, 15 hydrogens, and only 1 nitrogen. And so if we go through the same process and figure out its approximate molar mass, we have 10 carbons that are about 12 each, plus 15 hydrogens about 1 each, and then nitrogen, we get 149. So it's not methamphetamine either. So we go on to ecstasy. "11 carbons, 15 hydrogens, a nitrogen, and 2 oxygens." So cocaine had too many carbons, and that made it too heavy. And then methamphetamine didn't have enough, and so now this has an extra carbon and 2 extra oxygens, so it should weigh more than the methamphetamine. So we have 11 carbons, 15 hydrogens, nitrogen, and 2 oxygens for a total of, it's about 193. So 193 was about what our molar mass was. And so we can pretty much say that it's ecstasy, but let's go ahead and look at the heroin. Well, we can see automatically, if we look at heroin, its formula has 21 hydrogens, or 21 carbons, 23 hydrogens, a nitrogen, and 5 oxygens. Cocaine had less carbons, less hydrogens, and less oxygens, and weighed too much. So heroin, without even going into the molar mass, is going to be too heavy. And with morphine has 17 carbons, which is the same number that cocaine had, 19 hydrogens, a nitrogen, and 3 oxygens. So it has less oxygen. So let's just quickly see how it lines up. So we have 17 times 12 plus 19 plus 14 for nitrogen plus 3 times 16 for oxygen. So it's too heavy also. So the answer to the last question, does this data indicate that it may be cocaine, methamphetamine, ecstasy, heroin, or morphine, or none of these? Well, the data that we have just from the colligative property experiment indicates that it might be ecstasy. So that's the answer to that question.